In today's video, we are going to learn how to use Unity's job system to transform our existing code from the previous video to a code that utilizes jobs. We will start where we finished in the vlog video, so please watch that video first. We are starting this project with 2000 units and 13 FPS, and we will finish with 4000 units in the scene with 40 FPS. Let's begin. We will be using Unity 2019.2 for this project and a lightweight render pipeline. We will start with the finished project from the last video, so grab it from GitHub. The link is in the description below. Let's start. First, let's make sure that we have all of the necessary packages. So go to the package manager and search for the jobs package. Download the most recent version. Then search for the burst package and download it also. The job system works in a way that you declare a separate class that is responsible for the given calculations. We will create such a class, and in its constructor we will provide all of the necessary variables that this class will use for its calculations. Then we will schedule a job that will handle those calculations, and in the end we will use fields from the job class that got modified during the calculation and assign them to the monobehavior fields. So all of the behavior implementations in the flock script will have to be moved. We will erase all of them and write them again. We can also remove all of the class fields that are now not used. We will leave only those that are assigned from the inspector, and the speed, current velocity, the value that is used in the smooth dump method. Let's also leave the flock reference. Additionally, let's add getters for the field of view, smooth dump, and current velocity. In the flock script, we will clear the update method for now. Let's create our job class that will handle all of the behavior calculations. This class has to implement one of the iJob interfaces. Because we are going to work with a collection of units, we should use the interface called iJob parallel for. But first, let's add the necessary using statements for unity.jobs and unityengine.jobs. Now we can use the proper interface. Now go ahead and implement the interface and see what it looks like. As we can see, the iJob parallel for will take an integer in its parameter. This integer will refer the current unit that is currently in the iteration loop. So if we, for example, construct this class with a field that is a list of flock units, then the index in the parameter will be the index in that list that the job is currently using for calculations. Probably the most basic job interface is the iJob interface, and its method does not take any parameters. That means that this job cannot process collections at the same time. In our case, the flock is a collection of units, so we will use the iJob parallel for interface. We will start with declaring all of the necessary fields for the job class to calculate the move vector of every unit. Because we cannot pass a list of flock units, which are monobehaviors, we need to declare a collection for every single variable that we normally would just take from the transform of the monobehavior. The job class can only work with certain data types. So let's start with a collection that will hold forward vectors of all flock units. In the move job class, we can use a generic collection called native array. But first, we need to add a namespace called unity.collections. Now we can declare the first field, which will be a native array of type vector3 called unit forward directions. We will need similar collections to hold the current velocities, the variable for the smooth dump method, the positions of all the units, the cohesion neighbors, the avoidance neighbors, and lastly the alignment neighbors. Next, let's add a native array of floats for the speeds of all units and the speeds of neighbor units. We will also need a vector3 for the flock position. a vector3 for the player position, a float for the cohesion detection distance, a float for the avoidance detection distance, a float for the alignment detection distance, a float for the bounce distance, a float for the obstacle distance, a float for the cohesion weight, a float for the avoidance weight, a float for the bounce weight, another float for the obstacle weight, and also floats for the field of view angle, the minimum unit speed, the maximum unit speed, the smooth dump, and the delta time. Now, when we have all of the necessary fields, let's get to the method. We are going to follow the same steps as we did in the previous video. So first we will find all of the neighbors for the cohesion, avoidance, and alignment by checking the distances. Let's cache the current unit's position that the for loop is iterating through right now. Let's also cache the unit's position that the job is currently iterating through, and this will be the index from the method parameter. Now check the distances and add neighbors to the proper lists. We are going to go through the code pretty fast, so if you want to learn about the flocking algorithm, please watch the previous video. Next, we are going to calculate the speed of the unit by calculating an average speed of all units in the cohesion range. Now we will take care of the cohesion calculations. As we learned previously, a cohesion vector is calculated as a direction from a unit's position to the average world position of all units in the cohesion range. We also will check if a neighbor is in the field of view by calculating an angle between the unit's forward direction and the direction to the neighbor. We forgot to declare a field for the cohesion weight, so let's add that right now. Now the avoidance. Let's copy the code from the cohesion calculations, cause it will be pretty similar. We will of course change every variable that has word cohesion in its name to a corresponding variable for avoidance. The avoidance vector is calculated as an average vector from the unit's position to neighbors in the avoidance distance. Because we are adding a local vector in the loop and not the word position like in the cohesion, we don't have to subtract the unit position after the loop ends. Let's do the same for the alignment and change the variables. As you can see, I made a big mistake that will cause me later a lot of debugging. I forgot to change the avoidance vector to the alignment vector in the loop. As for alignment calculations, we calculate the alignment as the average vector of forward directions of the neighbors in the alignment range. We are not storing those direction vectors anywhere right now, so let's add a field for it. And in the place when we add the alignment neighbors to the array, let's also add their forward vector to our new array. Now add the forward vector to the alignment vector calculations. The next part will be declaring variables for a job instance and scheduling this job. We are going to do it every frame, so let's go to the update method. First, we will have to declare all of the arrays that we want to pass in the job constructor. So let's copy the fields from the job class and declare array instances from them. In the array constructor, we will provide the number of all units in the flock as the array length. We will also add an allocator.tempJob That means that this array will be discarded after the job is done. Let's do it for all of the arrays. In a for loop, we will fill the necessary arrays with current unit values. Those arrays will be unit forward directions, unit positions, unit current velocities, and all unit speeds. The rest of the arrays will be filled with values in our job, so let's initialize them with some default values. We need to add a getter for the variable speed in the flock unit script. Now we are going to schedule our job. So let's create a new job and initialize the class fields using newly created arrays. Now initialize the rest of the fields. First assign detection distances, then weights. The field of view angle will be equal to the field of view angle in the unit prefab. Now initialize the minimum speed, the maximum speed, and also the smoothAmp method value from the unit prefab. And initialize the delta time with time.deltaTime. To schedule a job, we have to call a method called schedule on our job instance. In the constructor, we have to pass the length of the whole array that should be calculated, so in our case the number of all units. Also an integer that defines how big of a batch this particular job should handle. Let's say 5 for now. This method returns an object of class jobHandle. We can use this object to check if our job has finished its work. Next, we can call a complete method on the job handle. By doing this, the job handle will ensure us that the job is completed, and on the next line of code, we can retrieve values from the job instance and know that the calculations were completed. Next, we will iterate through all of the flock units and modify them based on the data calculated in the job. So we will change the transform forward direction, the transform position, and the unit current velocity. Let's add a setter for the current velocity in the flock unit script. Also, we will update the unit speed value. The speed also needs a setter. Lastly, we have to dispose of all of the native arrays that we declared before we scheduled the job. We will just call a dispose method on every array. Now let's combine all of the behavior vectors into one. Let's use the smoothAmp method to get the move vector for this frame. Unity is telling us that we cannot pass an indexer as a parameter, so let's make a new variable for this value. And as you can see, I forgot to use the smoothAmp value in the smoothAmp method. We will fix this later. Now normalize the move vector and multiply it by speed. Let's add a simple check to see if all of the behaviors had no neighbors, and in that case the move vector will be equal to the forward vector of that unit. Now update the position by adding the move vector multiplied by delta time. Next, set the forward vector to the move vector and update the speed by the current velocity. Let's go back to Unity, find our fish prefab and set the inspector values. I will set the field of view to 270, the smoothAmp to 0.5. When we hit play, we are going to get a bunch of errors, but don't panic, it's all on purpose. We will learn something from all of them. Unity is telling us that the iJob parallel 4 has a restricted range. That range is declared in the job constructor. If you remember, we passed 5 as that range, so our job will have the available indexes from 0 to 4, second from 5 to 9, third from 10 to 13, and so on. A job will tell you that it cannot safely iterate through an array with an index outside of that range, but there is a way to tell the job this array is safe for you to iterate through even outside that range. Back in the job fields declaration, we can add an annotation to arrays called native disable parallel for restriction. Let's add those to our arrays. We forgot to add the smooth dump value in the smooth dump method, so let's fix that. Now hit play and let's look at the FPS number. We are getting 21 FPS, so a 60% increase. Pretty good, but we can do a lot better. The full power of the job system is used with the burst compiler, so let's enable it. What we have to do is to add the unity.burst namespace and add the burst compile annotation to the job class declaration. In Unity, go to jobs, burst, and enable compilation. Now hit play again. And there we go, 70 to 80 FPS with no stutters. That's what we wanted. We still have some problems with the fish movement. They are not turning, so let's go and fix that. First, we are assigning in the neighbor speed array the wrong value. We should get the speed of index I, not index. Secondly, as we noticed earlier, we are incrementing the avoidance vector in the alignment calculations. So let's fix that. In the meantime, I reduced the flock number to 1 to debug stuff better. Now when we hit play, we can see a working flock that reacts when we change the flock values in the inspector. So let's increase cohesion and see that our fish are grouping together. We can change distances. And let's increase avoidance to make our fish disperse. Next, in the execute method, after the alignment calculations, we will calculate a bounce vector. So let's calculate an offset to the center of the flock. We have to add a field for flock position in our job class. In the update, let's initialize this value to transform that position. Now we can declare a boolean value that will be true if the unit's distance to the center is 90% or more of the bounce radius. And once again, more in-depth analysis of the flocking algorithm can be found in the previous video. Next, declare a vector3 called bounce vector that will be equal to an offset to the center of the flock when a unit is near bounce. Otherwise, set this vector to vector3.0. Let's normalize this vector and multiply by the bounce weight. And in the end, add the bounce vector to the move vector. Save, go back to Unity, set bounce weight and distance, and hit play. Let's increase the avoidance weight to drive the fish away, and as we can see, when they get close to the bounce distance, they start turning away. The last thing I want to do is to randomize the flock behaviors at start so that flocks will not behave the same way. We will do it by simply randomizing weights, bounce distance, and minimum and maximum speed. Let's change the distances a little bit. Let's go back to Unity and duplicate the flock game object. I will create around 30 flocks, which will give us around 3000 units at the scene. There is one last issue I don't like. As we can see, our fish are grouping very tightly when the cohesion weight is high. To fix that, we will increase the smooth dump value on the fish prefab. So let's bump this value to 3 or something similar. After changing the lighting, adding some post-processing and giving the fish different colors, we have this final underwater scene. And that's it, guys. You can find the whole project on the GitHub in the description below. I hope you enjoyed it, and please like and subscribe if you like my content. There are new videos every Monday. Also, leave a comment. I'm happy to answer all of your questions. Take care.